This video will cover section 3.4, the substitution method for integration. The substitution method is one way of algebraically manipulating an integrand so that the rules apply. This is a way to unwind the chain rule for derivatives. When you find the derivative of a function using the chain rule, you end up with a product of something like the original function times the derivative. We can reverse this to write an integral. So if I take the derivative of the composition of f of g of x, by the chain rule, it's f prime of g of x times g prime of x dx. So if I integrate both sides of that, I end up with f of g of x is the integral of f prime of g of x times g prime of x dx, which makes a really nice substitution where we'll let u equal g of x so that du dx is g prime of x. And if we multiply both sides by dx, we have that du is g prime of x dx. Making these substitutions, the integral of f prime of g of x times g prime of x dx becomes the integral of f prime of u du, which will oftentimes be easier to integrate because we're just dealing with one function. Try substitution when you see a product in your integral, especially if you recognize one factor as the derivative of some part of the other factor. Let's take a look at some examples of indefinite integrals using the substitution method. In part A, we're looking at the integral of e to the 10 over x squared dx. While it doesn't look like a product, I could rewrite the integrand of this integral as e to the 10 over x times 1 over x squared dx, noting that this is the power of e to the x. Then it would be nice to make the substitution of u equal to 10 over x. And we'll take the derivative of both sides of that equation so that du equals negative 10 over x squared dx. Notice that I don't have a factor of 10 in my original integrand, so what I'll do is divide both sides by negative 10 so that the right-hand side of this equation looks like everything left over. I end up with negative 1/10 du equals 1 over x squared dx. And so we'll replace 10 over x with our u and 1 over x squared dx with our negative 1/10 du. This gives us the new integral e to the u times negative 1/10 du. From our properties of integrals, we can pull the constant multiple negative 1/10 out of the integral. And we're just looking at the indefinite integral of e to the u du, which we know from our rules of integrals is just e to the u plus c. You want to make sure that your final integral is always in terms of your original independent variable, which in this case is x. So we'll substitute back in for u. It's negative 1/10 e to the 10 over x plus c. So we substitute back in for u. Let's take a look at part B. We do have a product here. We have 6x squared times the square root of 3x cubed minus 1. There'll be no way to combine exponents here because the radicand is not the same as the base on the outside. So we will want to use the substitution method. We'll want to use the inner function 3x cubed minus 1 because we can see that it will power reduce when we take the derivative. So we'll let u equal 3x cubed minus 1 so that du equals 9x squared dx. Notice that we don't have a factor of 9 in our original. It's a 6, so I'll divide both sides by the 9. So we have 1/9 du equals x squared dx. So we'll be substituting for 3x squared minus 1, x squared, and dx. Our new integral will be 6 times the square root of u times 1/9 du. Again, we can pull the constant multiple out, 6 over 9, which is 2/3, the integral of u to the 1/2 if we rewrite the square root of u as its power form, so we can use the power formula for integrals. That's adding 1 to the power and then dividing by that new power. So we have 2/3 u to the 3/2 divided by 3/2 plus c because it's indefinite. This is 2/3 times 2/3 if we multiply by the reciprocal of the denominator times the square root of u cubed plus c. And then we want to make sure that our final antiderivative is in terms of our original independent variable, which was x. So we'll substitute back in for u. And we have 4/9 times the square root of 3x cubed minus 1 cubed plus c. And that's our final antiderivative for part B. Let's look at using the substitution method with definite integrals. When you use substitution to help evaluate a definite integral, you substitute for the limits of integration at the same time as you're substituting for everything inside the integral. If the original integral had endpoints at x equals a and x equals b, and we make the substitution u equals g of x, so that du is g prime of x dx, then the new integral will have the endpoints u equals g of a and u equals g of b. So you're substituting for this function g of u, and g is a function of x, so u will become functions of those x's as well. The nice thing about this method of changing limits of integration is you don't have to backtrack in your work. So you don't have to substitute back in for the original function, and then you don't have to substitute in for x's. You can just keep moving forward with this definite integral. So let's evaluate the definite integral from -2 to 2 of 2x over 1 plus x squared dx. Again, this isn't explicitly a product, but we could rewrite it as a product as the integral from -2 to 2 of 2x times 1 over 1 plus x squared dx. What you'll start to see as you do more practice is that whatever you choose to be u when you take the derivative should simplify to the other product. So I'm going to let u be the denominator, 1 plus x squared, so that du is 2x dx. And then I also need to work on changing the limits of integration. So my function here is 1 plus x squared. So I'll evaluate u at -2 and u at 2 to find my new limits of integration. That's 1 plus -2 squared, or 5. And this will be 1 plus 2 squared, which happens to also be 5. And so we're going to see what happens when we have the same limits of integration on an integral, which will lead us to a new property. So when I make my substitution, I have 1 over u du. Substituting in du for 2x dx, and then substituting in u and for the denominator. And we know from our rules of antiderivatives that the integral of 1 over u is the natural log of the absolute value of u plus c, and we'll evaluate from 5 to 5. So we're looking at the natural log of the absolute value of 5 plus c minus the natural log of 5 plus c, which ends up equaling 0. So we have two properties. One is that if the limits of integration on an integral are the same, the value is going to be 0, and we can see why. The other is if your function, if your integrand is negative, or I'm sorry, if your integrand is odd and it has a negative a to a, then your integral will be 0. That concludes this section on substitution. In the next video, we'll cover area, volume, and average value, which are all applications of the integral.